This video will calculate the force of the ground on a person as they're jumping. We have Jane practicing vertical leaping, and she can move her center of mass 0.6 meters off of the ground, higher than the ground. Her jumping action is to stand first, and then crouch down 0.18 meters, and then push upwards and straighten out her body. She's going to do this maintaining a constant contact force with the ground. That's going to be our assumption. And we're going to say that Jane has a mass of 60 kilograms. So we want to know, what is this contact force that pushes Jane up such that her center of mass is 0.6 meters higher? Well, she crouches down, the ground is in contact with Jane. Here we're just leaving the ground. So we're going to move forward here. There are 3 time periods to think about in this problem. It is important to recognize when you have a change in acceleration as we use kinematic equations. So we have the time when Jane is just at rest, standing on the ground. Her acceleration is 0 meters per second squared. During the uncrouching motion that I'm not showing really in this sketch, but uncrouching, moving the body upward, acceleration of Jane is upward, giving her some velocity upward, and the velocity when she is just leaving the ground, that'll be an initial velocity moving upward that we'll use to calculate the 0.6 meters higher. So 3 acceleration values. 0 acceleration here. There's some acceleration due to the push of the ground on Jane. And then there's minus 9.81 meters per second squared as Jane moves up away from the surface of the Earth. So first ask you a question, does the ground push upward on Jane before she jumps while she's at rest? And the answer is yes. The force upward on the ground equals Jane's weight. So we have mg and mg, and Jane is not accelerating here. There's a balance of forces. So moving on to part 2. The calculation of the force of the push on the ground, that number is equal to the ground's upward push on Jane. It's a Newton's third law situation. Contact of the ground acting upward on Jane, and now in this jumping motion, this upward force of the ground on Jane is larger than Jane's weight. So Jane's going to accelerate. I didn't have space to draw in Jane's picture in the middle here, and then she's going to leave the ground. So the upward force of the ground is greater than the weight. I'm going to work this problem with up being the positive direction, and it's time to apply Newton's second law. The net force is equal to the mass of the system multiplied by the acceleration. Well, for the net force, the force of the ground going up is one force. There's a downward force that acts on Jane, her weight. I just calculate that with the mass multiplied by the acceleration due to gravity. So that's the net force. We want to know the force of the ground on Jane. Well, we have Jane's mass. We know 9.81 for the magnitude of the acceleration due to gravity. How can we come up with the acceleration during this jumping action while Jane is moving up? Well, what we need to do is to take a look at this third part of the motion. The acceleration upward gives Jane a velocity Vy naught. This is just leaving the ground. There's going to be motion here. Jane is moving upward with this initial velocity in this part of the problem, Vy naught. The Vy naught is the velocity V sub y for this part of the motion. When Jane is jumping, or she's accelerating upward, at the instant she leaves the ground, she's achieved some upward velocity, V sub y. That connects us to this third part of the situation. That final velocity as a result of pushing on the ground, the jumping, is equal to the initial velocity when we're moving upward through the air. So let's take a look at what we have here. In the push-up from the ground, we achieve some final velocity in the y direction. This is the fourth kinematic equation. So that's Vy naught squared, Vy squared. Vy naught is 0 at the crouching. Jane has an upward velocity of 0 before she starts moving upward in the jumping action. And then 2, the acceleration for this time interval. Jane is said to move 0.18 meters upward. She's crouched down 0.18 meters. Now as she's about to leave the ground, she's moved up 0.18 meters, and her starting position was 0. So again, to emphasize, we're connecting the parts of the motion. This Vy naught in the third part of the motion is equal to the Vy that's achieved in the jumping action. Well, what is this Vy naught? We know how high Jane jumps. Her center of mass moves up 0.6 meters. For this part of the problem, we'll start the center of mass at a position of 0. Her center of mass is 0.6 meters at the top of the motion. The acceleration is the acceleration due to gravity, negative 9.81 meters per second squared. I'm working this problem as positive in the up direction, so the gravity gets a negative sign on it. And at the top of the motion, at the maximum height, what is Jane's velocity? It's 0. So looks like we'll be able to calculate Vy naught. Let's go ahead and advance the slide. So the final velocity at the top of the motion, Vy naught, that we want to know for this part of the motion. You should pause this and pull out your calculator. I came up with 11.772 meters squared per second squared for Vy naught squared, and then take a square root of that, 3.431 meters per second. I tend to write my final answer with 3 significant figures. For intermediate results, if I have to write it down on paper, this intermediate result, I write it down with 4 digits as kind of a guard digit, prevent round-off errors from rounding too much. If I'm using a calculator, I wouldn't even bother to round at all. I'll just use what's on the display of the calculator. So we've got this initial velocity moving upward after the jumping action. Now go back to this middle part of the motion when Jane is just leaving the ground. This final Vy naught squared, well, that's the Vy naught from the third part of the motion. The velocity upward just leaving the ground, that's equal to the initial velocity of Jane. It should be drawn down here, but we know this number, 3.431. And then we have 2 times 0.18, we get 0.36, and the acceleration upward can be calculated. 32 meters per second squared is Jane's acceleration value upward. It's a positive. What about the net force in MA? Back to that, the force of the ground upward minus the weight is a downward force equals mass times acceleration. So the force of the ground minus 60 kilograms, Jane's mass, times 9.81, that's the mg, and then Jane's mass times her actual acceleration. And again, pause this, I got 2,550 newtons for the force of the ground on Jane. Converting that to pounds, I got 574 pounds, which seemed a little large to me, but it's not out of bounds for an athletic person. And then I fed this problem statement into the Google AI, and it came up with 2,551 newtons. So we're going to take 2,550 as the good answer. So if you want to look at my list of YouTube videos, go to my website, gpclements.com. My videos are listed, organized in groupings by topic, and they're annotated. The title of the video, how long it is, how many minutes, and a brief description of the video. Physics and astronomy and some other miscellaneous topic videos are listed there. Everything there is free. You're not allowed to resell it, but you don't pay me, you don't register, you don't give me your name, you don't give me your email address, and my website does not put cookies on your computer. So keep working physics problems. Ask your instructor if you have a question.